Okay. So this is a Zoom meeting for Physics 231C. And we'll have a Zoom meeting like this every Friday, where the main purpose is to look at some of the homework problems that are coming due. Provide some hints on how to do the problems. There are hints in the supplemental content, but they're not, they're just written hints. So these will go over a little more the step-by-step process for doing a problem. And we'll pick out some of the more difficult problems in the assignment. Okay, so all the materials for the course are available on Lon Kappa. Log in at lonkappa.msu.edu. Hopefully you've already done that. You can look at the syllabus there. You can look at the various problem assignments. There's reading quiz number 0, which is due today. And there's problem set number 0, which is due next Tuesday. So most people have already done the reading quiz. You start by reading the chapter. This first chapter is fairly short. But anyway, you start by reading the chapter, and then once you've got the ideas and the equations that you'll be using, then you do the reading quiz. The reading quiz is meant to be pretty short. They're just short answer questions. A lot of them are multiple choice. And then the problem set is much longer. So the reading quiz might take a half an hour, but the problem set might take several hours. And as I say, there are hints in the supplemental content, so you can look at hints if you get stuck on a problem. Here's kind of an overview for the semester. The first part is on motion, and there are 3 chapters, 1, 2, 3. The next part is on force and energy, and there are 3 chapters, 4, 5, 6. We'll have the first exam after chapter 4. So the first exam will appear, in about the 4th week of classes. Then after these general subjects, the next part of the course is several different examples. So those will be chapters 7, 8, 9, 10. And then the last part of the course, the last 3 weeks, I guess, will be on motion again, but specifically motion of atoms. Up here, we're talking about motion of objects that you might see in everyday life, like the motion of a car or the motion of a baseball. Atoms are a bit different because they're so tiny. So we describe the motion of atoms using what's called thermodynamics. And that'll be the last part of the course. That's in, I guess, April. There's about 1 chapter each week, and the material is cumulative. You depend on the previous chapters for each new chapter. So don't skip a chapter, because then you won't be well prepared for the next chapter. Now, you have to read the chapter, and as you're reading the chapter, you should take notes. So you should have a physics notebook, which you only use for your physics course, and take notes as you read the chapter. mostly equations. Write down, as you read through the chapter, try to identify the most important equations, the most basic equations, and write them down in your notebook. So you'll have an easy way to look those up if you need to look them up to do a homework problem or on the exam. So this first chapter is on measurements. It's really just a review of math. There's not very much physics in this first chapter. It's mostly just math. But physics is a mathematical science. It concerns quantitative measurements. So some of the things you need to learn is how to describe measurements. There's a number and a unit. If you don't give the unit, you haven't described the measurement. I mean, suppose I tell you an object has a length of 3. Well, that doesn't tell you anything, because is it 3 inches? Is it 3 feet, 3 meters, 3 centimeters? It's not a information unless you give the unit. And when you do a calculation, you'll be calculating using numbers with units. So keep track of the units. Just not a question of plugging in numbers into your calculator. That'll end up with a number, but it won't tell you what the unit is. So you have to keep track of the units as you do the calculation. So do the calculation on paper. For each assignment, you should have the calculations for that assignment in your physics notebook. And as you write down the calculation, include the units and keep those units like algebraic quantities. And then when you combine the units, you combine the numbers with your calculator, but you'll combine the units by just looking at the units that are written down. That final unit will be the unit for the answer. Well, okay, so that's units. There are the prefixes like kilograms. Kilograms is 1,000. Mega is million. Micro is 10 to the minus 6. You have to be able to convert units. Maybe you'll be given information in miles and hours. Maybe you're told a car is going 60 miles per hour. How fast is it going in meters per second? Well, you have to know how to convert from miles to meters and hours to seconds. Now, everybody knows how many seconds are in an hour. 1 hour is 60 minutes. Each minute is 60 seconds. So 1 hour is 60 times 60, or 3,600 seconds. And not everybody knows how many meters there are in a mile, but it so happens it's 1,609. You can look up things like this in Google if you forget. So 60 miles per hour is 60 miles. That's 1,609 meters in the numerator per hour. So that's 3,600 seconds in the denominator. So now you see you have a number, 60 times 1,609 divided by 3,600. You use your calculator to calculate that. That'll turn out to be 26.8. And there's a unit. And you see what the unit is. It's meters in the numerator, seconds in the denominator. So when you do a calculation, keep the units as you write down the calculation. And then that will immediately tell you what the correct unit is in the answer. Now, of course, this is the appropriate unit because it's a velocity, distance over time, or meters per second. So that's the appropriate unit. So this is actually a way to double check that your calculation is correct. You have to be careful about significant figures. You probably studied those in high school. All right. So now let's take a look at problem set 0. That's the problem set which is due next Tuesday. It's from chapter 1 in the textbook. And here's one of the problems on the problem set. It's problem 63 in chapter 1. There are about 100 problems in each chapter, but we're not going to assign all of them. We'll assign maybe, I don't know, 5 or 10 of them. But this is a problem from the end of the chapter 1. It says, approximate planet Saturn as a sphere. You can neglect the rings. With a mass m and a radius r. And then the first part of the problem is calculate the mean density. And then the second part of the problem is the density of water is 1,000 kilograms per cubic meter. A cubic meter of water, try to picture the size of a cubic meter. Take a meter stick in 3 dimensions. Length 1 meter, width 1 meter, height 1 meter. So that's a meter cubed, the volume. That weighs a ton. That weighs 1,000 kilograms, which is a metric ton. And well, the second part of part B is, how does the density of Saturn compare to water? So you have to know the formula for density. You're going to calculate a density. So what's density? Well, density is mass divided by volume. Probably studied that in chemistry. But anyway, this is explained in chapter 1, if you're not familiar with it. Density, we usually call density the Greek letter rho, is the mass of an object divided by the volume of the object. Now it says Saturn is a sphere, so you have to know the volume of a sphere. Well, the volume of a sphere is 4/3 pi r cubed. So, you'll have to know all of these necessary mathematical expressions. You can look in the textbook in the Appendix A. Appendix A has a bunch of mathematical formulas, mathematical expressions that you're familiar with already, but in case you need any review or any reminder, you can look it up in the end of the textbook in the appendix. Now you can already see what the units of density will be. The numerator here is mass, so that'll be kilograms. We use standard units. And the denominator is volume. Well, the unit of volume is a cubic meter. So the units of rho will be kilograms per cubic meter. Now the question is, what's the number? So you'll have to look up the mass of Saturn. It turns out there's an Appendix E, which gives some astronomical numbers, but it turns out the value of m for Saturn is wrong. So don't use the value of m that you find in Appendix E. Just do a Google search. Type into Google, what's the mass of Saturn? And what you'll find is, well, it's something like 6 times 10 to the 26 kilograms. Get it more accurately. Get at least 3 place accuracy. But just for the purpose of this explanation, let's just say it's 6 times 10 to the power 26 kilograms. An enormous number in terms of kilograms. I mean, kilogram is sort of a human-sized number. Well, Saturn's a lot bigger than a human, so it's going to be many orders of magnitude, many powers of 10 bigger than a kilogram. So it's 6 times 10 to the 26 kilograms. The other thing you need is the radius of Saturn. And, astronomers look through telescope, see the size of Saturn in their telescope, figure out how big the magnification is, then they can determine how big the radius is. And if you look it up on a Google search, let's say, it's about 60 times 10 to the 6 meters. What's the radius of the Earth? It's about 6,000, it's approximately 6,000 kilometers. So that would be 6 times 10 to the third meters. Well, the radius of Saturn is about 10 times larger. It's 60 times 10 to the sixth in meters. All right, so now the rest is just math. You want to calculate rho, it's the mass, that's 6 times 10 to the 26 with its unit, kilogram. And in the denominator, the volume, that's 4/3 pi r cubed. Here's r. And here's its unit, meters cubed. So the answer to the calculation, this is the calculation you write down in your notebook. So far, you haven't touched your calculator. A lot of students make the mistake of starting a problem by punching numbers into their calculator. That's the wrong way to go about doing it. You don't pick up your calculator the first thing in approaching a problem. It's the last thing you do in approaching a problem. So first of all, you pick up your pencil and you write down, what am I trying to calculate? Well, I'm trying to calculate this number divided by this number. And don't forget the units. So now the answer will be a number with a unit. And we can see what the unit is. It's kilograms in the numerator and cubic meters in the denominator. So the unit will be kilograms per cubic meter, which we already saw that would be true. Now it's the number. So you have your calculator, you have 6 exponent 26, 4/3 pi is in the denominator, 6 exponential 7 cubed. And, try it with your calculator, you'll get a number, which is about 700. I'm just making a rough estimate here. So I don't write equals here because it's not exact. But it's roughly 700 kilograms per cubic meter. Now, of course, when you do it, you'll have to be more accurate. You're going to type this answer into ln kappa, and that'll require an accuracy of probably 3 significant figures. It has to be sort of accurate to 1% accuracy. So usually 3 significant figures is accurate enough. If you give too many significant figures, then ln kappa won't accept it. Ln kappa will say, no, don't use so many significant figures. I mean, after all, you only made rough estimates for these. So use 3 significant figures. And then if ln kappa tells you your answer is wrong, you might try giving one more significant figure. It might be, well, if you wrote down 710, it'd probably tell you it's wrong. So you'd have to be more accurate than just. So try to be accurate enough. All right, well, that's part A. Part A is done. And what about part B? Well, we'll want to compare that to the density of water, 1,000 kilograms per cubic meter. This has a density of 700 kilograms per cubic meter. So in other words, Saturn is less dense than water. If you had a big enough ocean, Saturn would float because its density is less than the density of water. Of course, can't really happen. How is it possible for the density to be less than the density of water? Well, most of Saturn is gas. Those major planets on the outskirts of the solar system are called gas giants because they're not solid like the Earth. They're more like a gas. All right, so that's an example from the textbook. Let's see if there are any questions. So let me look on the meeting chat board. I don't see any questions in the chat board. Anybody want to mute your microphone and ask a question? Or if you want to ask a question, you can just type it into the meeting chat on Zoom. Okay, well, that's an easy one. Let's go to problem 65. Read something like this. In 1973, the horse Secretariat ran 1.5 miles in 2 minutes and 24 seconds in the Belmont Stakes. Part A, what was his average speed? And give the answer not in miles per hour. That wouldn't make any sense. And horses don't go many miles per hour. It wouldn't really make any sense to talk about, centimeters per second or anything like that. Use standard units. It makes sense to give the answer in standard units, which are sort of human-sized units or horse-sized units. So we'll give the answer in SI units. That's part A. Then there's a part B, which is to calculate something else, which I didn't copy here. So let's just see how to do part A. You have to know what's meant by average speed. Average speed is distance divided by time. Now, we don't write d over t because that's ambiguous. We write delta s over delta t. We use this delta notation. And this will be very common throughout the whole semester, is to use this delta notation. If you see delta Q with the Greek letter, capital letter delta, delta Q means a change of Q, where Q is some quantity. In this case, Q is a distance or a position. Actually, here, S is the distance from the starting point. Delta S is the change in the distance from the starting point. Or here, T is the time. So let's say the time starts at, 12 noon. And then he rides, he gallops for 2 minutes and 24 seconds. So the time would then be 12 noon plus 2 minutes plus 24 seconds. 2 minutes and 24 seconds after noon. Delta T would be the change of the time. It started out at 12 noon. It ended up at 12 noon and 2 and 24 seconds. 2 minutes and 24 seconds. So delta T would be this 2 minutes and 24 seconds. So the delta notation is when you see a Greek letter delta, that means the change of the quantity that delta is modifying. A change of Q. So delta is not something that multiplies Q. Delta is more like an operator. It's not a quantity delta multiplied by a quantity Q. No, delta Q is one quantity. It's the difference between two quantities. It's the final Q minus the initial Q. It's the change of Q. If Q changes from the initial value to the final value, then the change of Q is Q final minus Q initial. And we write that as delta Q. But don't be confused that delta is some number with a unit. It doesn't have any unit. It's not even a number. It's more like an operator. It operates on Q. It tells you, I'm talking about the change in Q. It's just a shorthand. I could write everything out in terms of differences, but that would make this, a long, complicated looking quantity expression. If I just write it as delta S over delta T, it's a very simple looking expression. All right, so that's the basic equation. So now we have to do the calculation. S initial is the distance from the starting point. Well, that's 0 initially. S final is the final distance. In other words, it's the final distance that the horse has galloped. It's the distance that it's traveled from the starting point. What says here, it ran 1.5 miles. So S final would be 1.5 miles from the starting point. Then delta S is S final minus S initial. Well, in this case, S initial is 0, so delta S is just S final. So I could have written this as S final over T final, but it's a little easier if you keep track of the fact that, it's a change in position divided by a change in time. This is the change. You have your stopwatch, and you have your pocket watch, and you see how did the time change. So that's delta S. Now what's delta T? 2 minutes and 24 seconds. Well, we're going to get this in SI units, so we better put all the times in SI units. The standard unit of time is a second. So I better write out delta T not as 2 minutes plus 24 seconds, but as 2 times 60 seconds plus 24 seconds. In other words, 144 seconds. I really ought to put in the unit here. So delta T is 144 seconds. That's 2 minutes and 24 seconds. Converted all into seconds. Because if you start mixing up different units, especially when you're adding quantities, that gets very awkward. So especially when you're adding quantities, you convert all the units to one unit. In this case, the standard unit, seconds. All right, so I have delta S over delta T, but I've got delta S here in terms of miles. I want delta S divided by delta T, not in miles, but in meters. That's SI units. So I remember 1 mile is 1,609 meters. What if you can't remember that? Well, you can always look it up in the book, or you can write it down in your physics notebook. As you're reading the chapter, you can write down things like that. So you can just look back up in your notes, or you can always just do a Google search. 1 mile is 1,609 meters. We already have this in seconds. So far, we haven't touched our calculator. You don't start by punching numbers into your calculator. That's not the first thing you do on any physics problem. The first thing you do on any physics problem is pick up your pencil and write down the equations. And then once you've got the equations written down and reduced down to the form that you can calculate it with your calculator, then you pick up your calculator. So we can say delta S over delta T is, well, in the numerator, we have 1.5 miles, and for miles, we'll put in 1,609 meters. And in the denominator, we have delta T, which is 144 seconds. So you put in 144 seconds. So you see how we write this equation in your physics notebook, keeping track of the units. Don't drop the units. It's useful to have the unit written with the numbers. But after all, the numerator here is not 1.5 times 1,609. That's not the numerator, because that's just a number. But the numerator is a distance. So unless I tell you what the unit is, the number doesn't mean anything. So you write it down as 1.5 times 1,609 meters. And the denominator is not 144, because that's just a number. But the denominator is supposed to be a time interval. So I have to say, is it 144 hours, 144 minutes? No, it's 144 seconds. So if you always keep track of the units in doing the calculation, you'll see what the final answer is going to be. The final answer is going to be a number with a unit of meters per second. That's the appropriate unit for a velocity. Velocity has the same units as speed, distance over time. Now you have to calculate the number. Well, okay, here is where you pick up your calculator, but not until you've got this equation written down in your notebook so that you can see what you're going to calculate. So you're going to calculate 1.5 times 1609. So that's more or less 1600 plus 800. So that's more or less 2400 divided by 14 divided by 144. So this is like 24 times 100. This is like 1.4 times 100. So that's going to be like, I don't know, 16 or so. Powers of 100 will cancel. It'll be something like 16 meters per second. But you have to do it accurately. So that's why you need a calculator, because you're not going to try to do this algebra or this arithmetic in your head. Okay, so that's all I've got written down here. Use your calculator, calculate this number, and it'll be something like, I don't know, 16 or 18 meters per second. And part two is to calculate something else. That's to calculate the speed of a human sprinter. You know, Secretariat, one of the fastest horses in history, could run at this speed, about 16 meters per second. How fast can a human sprinter run? Well, a human sprinter runs 100 meters in 10 seconds. The world record for the 100-meter dash is about 10 seconds. So a human sprinter can run 100 meters in 10 seconds. So the velocity is 100 over 10 meters per second. So 10 meters per second. So Secretariat could run faster than a sprinter over this kind of distance. It probably says compare the two numbers. That might mean what's the ratio. I'm not sure what that means, but anyway, you should be able to tell from the statement of the problem what you're going to put in the answer box for part B. All right, any questions? I don't see any questions, but you know, be sure you understand this delta notation. Read about that carefully in the textbook. Here's another problem. It's problem 86. This is a problem for the Flat Earth Society. Who measured the radius of the Earth? Of course, the Flat Earth Society says the Earth is not round. You know, it's flat. So according to the Flat Earth Society, there's no meaning to the radius of the Earth. The Earth is not a sphere with a radius. But of course, we all know the Earth is a sphere. It's not a flat plane. One of the first people to understand that the Earth is a sphere, you know, if I go out in a field and I look around me, it looks like the Earth is just a plane. Well, that's because the radius is very large. So if I go out in a cornfield or something, or if I go out in a wheat field or something, and I look in all directions, all I see is a flat plane. I say the Earth is flat. But that's because I'm only able to see over a short distance. If I could see over thousands of miles, then I would see that the Earth has curvature, and it's actually a sphere. Who was the first person to really understand that the Earth is a sphere? Well, it was Aristotle, the famous philosopher of the ancient Greek Empire. Aristotle noticed that when there's a lunar eclipse, when the surface of the Earth, or when the Earth is in between the sun and the moon at a full moon, the Earth's shadow can land on the moon. So then you're seeing the moon not as a full round moon, but you're seeing it partially covered by the Earth's shadow. And Aristotle noticed that the shape of the shadow has some curvature. And that's because the Earth is not flat, it's a sphere. Okay, so even in the time of Aristotle, it was understood that the Earth is round. But who measured the size of it? You know, when Christopher Columbus sailed west on the Atlantic Ocean, the people told him, Christopher, don't sail west. You'll come to the edge of the Earth. You'll fall off the edge of the Earth because the Earth is flat. Well, of course, the knowledgeable people knew that the Earth was not flat, but unknowledgeable people would tell Christopher Columbus, don't just sail off to the west, you'll come to the edge of the Earth and fall off. Well, Columbus knew the Earth was not flat, so, but did he know the radius of the Earth? Yeah, Columbus knew the radius of the Earth. He wasn't the first person to determine the radius of the Earth. Who was the first person to determine the radius of the Earth? Well, it was another Greek philosopher. I guess it was Eratosthenes of Cyrene. He was Greek, he lived in Egypt, but in his time, Egypt was part of the Greek Empire. You know, after the Greek Empire conquered Egypt, Egypt was then part of the Greek Empire. And so there were Greek philosophers, mathematicians, scientists living in Egypt. And this man, Eratosthenes, figured out a way to determine the radius of the Earth. He lived 276 to 194 BC. So we're talking about, hundreds, really thousands of years ago. That would be 200 years before the life of Jesus of Nazareth. Now, how did he do it? Well, he did it by looking at the position of the sun at noon at two different points on the Earth. So you can read about this in the problem. The problem has a little paragraph about Eratosthenes and his observations. If he considered his hometown, that's Cyrene, at noon, midsummer's day, the sun would be directly overhead. Now, he had an assistant who walked over to another city, the city of Alexandria, and at a very same time of day, looked at the position of the sun. Well, it won't be directly overhead. It'll be at a somewhat of an angle south of the direction directly overhead, because he walked north from Cyrene to Alexandria. So he could measure this angle. He could measure this angle. Let's see if I can indicate which angle I'm talking about. Here's the angle that he could look at. He could say, okay, let me look at noon, midsummer's day, and the sun is not exactly overhead. It's a little bit below overhead. It's some angle about 7 degrees below the direction directly overhead. So this angle would then be known. And let's just call that theta. Oops. So we'll call that angle theta. It's about 7 degrees. He also knew how far did he walk. So he measured how far is it from Cyrene to Alexandria. And that's a few hundred miles. Now, if you look at the geometry of this drawing, this angle is the very same as this angle. So this angle is also 7 degrees, because by high school geometry, you have a line cutting parallel lines, then the corresponding angles are equal. So this angle, which he measured, was theta, but he also knew that also has to be the distance or the angle of these vectors from the center of the Earth to Cyrene compared to the center of the Earth to Alexandria. Now, theta, the definition of an angle is that the arc length is the radius times the angle, where the angle is given in radians. So we have this formula, we have this equation, which comes from this little geometrical drawing here. The arc length is the radius times the angle in radians. For example, if you had an arc length all the way around the Earth, the arc length would be 2 pi r. That would just be the circumference of the Earth. 2 pi would be the angle in radians. 2 pi radians corresponds to 1 complete revolution. Now, this is only a fraction of 2 pi radians. It's 7.2 degrees, but you'd have to convert that into radians. So in any physics problem, you have an equation. You have to calculate something with an equation. So here's the equation. It's really just the definition of an angle in radians. And again, if you're not so familiar with angular units like degrees and radians, you can look it up in Appendix A in the textbook. Now, your calculator can be converted between degrees and radians. Right? There's a button on your calculator which tells whether you're calculating an angle in degrees or an angle in radians. Well, you want to use this equation. What you want to know is r, the radius of the Earth. That's what Eratosthenes was calculating. So the answer is r is s, divide both sides of the equation by theta, r is s divided by theta. S was the measurement of the distance to go from the city Cyrene to the city Alexandria. So S is a number that we know. Theta is this angle, which in degrees is 7 degrees. You have to convert that into radians. And R is just S divided by theta. So that's the answer to the question. That's the calculation that Eratosthenes did. And you're going to do that calculation. And, of course, there's always an uncertainty in all measurements. So, maybe his assistant didn't measure this distance very accurately or didn't measure the angle very accurately. It's only given to, I think, 2 significant figures. So you get a value for R, which is somewhat uncertain. But anyway, it'll be about right. And that's the point that Eratosthenes determined the radius of the Earth. Not to great accuracy, but, the radius of the Earth is about 4,000 miles. It's a little less than 4,000 miles. And that's the number that Eratosthenes calculated. All right, so you need to read chapter 1, take notes, do the reading quiz, which is due tonight. A lot of people have already finished it because the questions there are fairly simple. They're just multiple choice questions. And then the problem set is about, I don't know, more, or something like 10 questions. A little more difficult, at least some of them are. So that's due tonight. And the problem set is due Tuesday. Now, as with all the assignments in this course, don't try to do it all in one sitting. Don't try to, it's due Tuesday night. Don't start working on it Tuesday afternoon. It's going to take you longer than that to do all the problems. This first assignment's pretty short. But for the later assignments, you really have to spread the assignment out into several days. Rather do 2 hours each day for 3 days than try to do all 6 hours the day that it's due. All right, any questions? I don't see any questions on the chat. Some students in this course are freshmen. The majority are sophomores and juniors. The sophomores and juniors, if they're studying some kind of science, have probably used ln kappa before. So ln kappa is pretty familiar, but it'll take a little while to get used to using ln kappa. So this first assignment, the main purpose is just to get some practice using ln kappa. And then the next chapter, chapter 2, is where we start with physics. All right, well, we're supposed to take about an hour, maybe a little less than an hour, maybe 45 minutes. So I'm more or less. Okay, so here's somebody put a question in the meeting chat. How do you put a ratio in ln kappa? Well, a ratio is just a fraction. Suppose you have 2 numbers, A and B. And you want to know what's the ratio of A to B. So what is the ratio? What's the meaning of the word ratio? It's just a fraction. So the ratio is A divided by B. Now, when you calculate ratios, these have the same units. A might be a distance, B would also be a distance. You want to compare those 2 distances. Or A might be a speed, B might be a different speed. You want to compare the 2 speeds. Or we had in the problem on Saturn, you might have the ratio of 2 densities. So you have the density of Saturn, the density of water. What's the ratio of the density of Saturn to the density of water? Well, it's just A divided by B. Now, A is a number with a unit. B is a number with the same unit. So you're going to have a unit in the numerator and the very same unit in the denominator. So the units cancel. So it'll just be a number. So a ratio will just be a pure number. And so how do you put that in ln kappa? Well, in the box, in the answer box, you just type that number. And no unit. Here's somebody's asked a question. So would a correct ratio be written as 7 meters or 4 meters over 7 meters? No. 4 meters divided by 7 meters would not be a correct answer for ln kappa, because that kappa is looking for a number. So you have to simplify. You have to simplify this. So, how do you simplify this? Well, oops. In your notebook, you could simplify it this way. You could say, well, I'm going to cancel the m and I'm going to cancel the m. So the answer is 4 divided by 7. Now, you could try typing into ln kappa 4 divided by 7, but it won't accept that. It wants a number. It doesn't want an arithmetic calculation to do. So you would have to convert this into a real number. So it would be, well, let's see, 4 divided by 8 would be 0.5. This will be a little bit bigger than 0.5. So I don't know, maybe it's 0.6, 0.63 or something. So this is what you type into ln kappa. The number. Let's see, somebody has written a question. Can you explain what type of answer we need for 147 and 148? I read the hint, however, what I am thinking would be the answer is not working, and I'm wondering if I could just interpreting wrong. Well, what is problem 147? Well, let's see if I can actually go to ln kappa. No, I don't want that. I want ln kappa. Problem set 147. 147 is, oh, no, that's the wrong class. Hold on a second. One 147. Here's 148. Oh, this is a formula response. So you want to put in here a formula without any numerical factors. Oh, I see. That's 147, 148. So you want to put in here a formula. You want to type in a formula. Now, how do you type a formula into ln kappa? Well, if you haven't done this before, you go to supplemental content. Look at the FAQ folder. I don't know how to use ln kappa. Okay. Here's how you type formulas into ln kappa. Most of the questions will have numbers as their answers. with units, but a few questions ask for formulas. Keep the following in mind. The standard symbols for arithmetic are plus, minus, star, divide to the power. Addition, subtraction, multiplication, division, exponentiation. You can use parentheses for grouping, but not brackets or curly brackets. The standard order of operations applies. You must always explicitly indicate multiplication. So your answer might be 3 times y times z. You can't type the answer 3yz. 3 times y times z. And you won't have a number for y. Y will be an arbitrary symbol to stand for something. Don't rename variables, use variables that are given in the problem. Well, unfortunately, I can't look at the actual problem unless I have the book. So if I go back to the problem, 147, 148, do problem 147. Problem 147, I can tell you where you can read about this. This is the section about what's called this is section, I'll tell you what section it is. It's the section which is called dimensional analysis. Section 1.3. Section 1.3, the part which is called dimensional analysis, is what's going to help you to do this problem. But basically you have this quantity, K, which will have some units. And you'll have this quantity, M, which will have some units. And you want a combination of those two things, which have the units of seconds. I think this is asking for the period of oscillation. So yeah, what's the period? Well, period is in seconds. So you want to make a combination of K and M, which will have units of seconds. Now, K has units of newtons per meter or kilogram meters squared, no, kilograms per second squared. So K will have units of kilogram per second squared. M will have units of kilograms. It's a mass. So mass has units of kilograms. K is a force divided by a mass. It'll have units of kilogram divided by second squared. So if I take K divided by M, or if I take M divided by K, that'll have units of second squared. And if I take the square root of that, that'll have units of seconds. And that's the correct unit for period. So the formula, which will have the right units, is the square root of M over K. That's what you want to put in here. The square root of M over K. So, you know, you could try something like the square root of M over K. This shows, let's see, this shows what I put in. I put in the square root M over K. You are correct. So that's correct. It's got no numbers in there, just these symbols. But the symbols have to have the right unit to be a time, because period is a time. A good way to get answers on questions is to type questions into the discussion board. You know, post a discussion. How do I input the answer? See FAQ number 10. Send that. Now, when you go back to now, when I go back to that problem, I'll see there's a that's Eratosthenes. Here's the formula responses. So this is formula responses. There's a bubble here. So the bubble will be that question. And that'll tell you how you input. Somebody will have to answer this for you, but if you type in the question, then presumably somebody will answer it, and then that'll help you know how to do it. All right, so let's see what happened to the. What I'm inputting is this, 2 pi square root of m over k. It says without numbers. Apart from numerical factors means don't include any numerical factors. 2 pi is a numerical factor. Anyway, 2 pi won't be understood. If you read FAQ 10, you always have to put a multiplication sign if you're multiplying two different numbers. So if you tried 2 times pi times the square root of m over k, that'd be more or less correct, but it's not apart from numerical factors, so that probably wouldn't be correct. Okay, so we've gone over an hour now, so I think I will end the meeting. Let's see, what do I want to do? I want to stop the recording.